The hurricane is still offshore. The eye has not crossed land. Yet water is already climbing over roads, filling bays and cutting off exits. The coastline is flooding before the event most people call landfall. That is not an early arrival of the eye. It is the ocean responding to hours of wind across a storm-sized area. Water has momentum, coastlines have shape, and neither waits for the center dot to touch shore. Before Hurricane Ike reached Galveston in 2008, water levels had already risen across the northwestern Gulf. In some places, the sea was many feet above normal, while the center remained offshore. The common picture puts all the danger inside the eye wall. Storm surge works on a different geometry. It begins with a broad wind field, and builds wherever that wind pushes water toward land. Why can the ocean rise so early? Why do neighboring stretches of coast get very different water levels? And why is the hurricane's central pressure only a small part of the answer? To see it, we will follow one parcel of water from the open ocean across the continental shelf, into a narrowing bay, and finally on top of the normal tide. By the time the eye reaches land, the surge is not starting. It is the visible result of a system that may have been loading the coast for a day. That early loading changes the practical clock. A road can become impassable while the sky still looks merely bad, and an evacuation route can close before the forecast's landfall time. The center is a useful location marker, but water responds to the entire wind field. Storm surge is the abnormal rise of water, generated by a storm above the level the tide alone would have produced. It is a change in the ocean surface, not a single breaking wave. Add the astronomical tide to surge, and you get storm tide. Add waves, wave setup, rainfall and river flow, and you get the total water level that structures and roads actually experience. These terms matter because several layers can peak at different times. A modest surge near high tide can become more damaging than a larger surge near low tide. Surge is measured vertically, while inundation describes how deeply that water covers normally dry ground. Elevation, dunes, levees, roads, canals and drainage determine how far it spreads inland. Waves ride on top of the raised water. Their impact reaches higher structures than the smooth surge level, and repeated breaking can add water near the shore through wave setup. Rainfall is separate again. Fresh water can meet salt water moving inland, especially around rivers and bays. The combined flood can exceed what either source would produce alone. So the coastline does not receive one wall of water, it receives a changing stack. The first and largest driver of the surge layer is usually wind. Separating the layers also prevents a common mistake after the storm. A high water mark records the combined water that reached a place. Scientists then use gauges, wave records, tide predictions, and field surveys to estimate how much came from each part. Air moving over the ocean pulls on the surface through friction, ripples become waves, surface currents begin to drift, and momentum transfers from the atmosphere into the water. One gust has little effect. A hurricane supplies a broad, persistent wind field. The same direction can blow over hundreds of miles of water for many hours. In the northern hemisphere, a moving hurricane often produces its strongest onshore push on the right side of its track. Storm motion adds to the rotating wind there. The longer the fetch and duration, the more time water has to organize into currents and waves. A large hurricane can begin moving the coastal ocean while its eye is still far away. The wind does not push every parcel straight toward land. Earth's rotation, friction, depth, and coastline shape bend the flow, but the net transport can still pile water against shore. This is why storm size matters. A larger wind field acts on more ocean. Peak wind helps set the force, while footprint and duration set how much water participates. Expand the cyan wind ribbons over the dark Gulf. The arrows become a continuous surface current, then the current becomes a broad moving slab. The ocean has started traveling before the storm center does. Every part of that slab does not move at the same speed or direction. The useful point is the accumulated transport. When onshore flow persists over a large area, the coast receives water faster than the local ocean can redistribute it. Far offshore, the ocean is deep. Wind-driven circulation can extend downward as well as horizontally. So the surface rise may be subtle even while a large volume of water is moving. Think of a rotating conveyor. Surface water moves one way, deeper water can return another way, and the full circulation fits inside the deep water column. As the storm approaches land, the seafloor rises, the water column becomes thinner, and that deep return path is squeezed. The bottom interrupts the vertical circulation. Water that cannot continue downward must spread sideways or upward. With onshore wind still pushing, more of it collects near the coast. The same volume now occupies shallower space. The surface lifts, currents accelerate through channels, and the surge becomes visible at tide gauges. None of this requires the eye to cross the beach. The shelf begins miles offshore, so the bottleneck begins while the center is still over water. Cut the ocean open. The deep conveyor compresses against the rising shelf, its return lane collapses, and the displaced water climbs the coastal wall. The cross-section explains why satellite views can be deceptive. Offshore, a small change in surface height spread across a huge area stores an enormous water volume. As that volume enters shallow water, the same excess becomes concentrated and easier to see. A wide, gently sloping continental shelf forces the incoming flow through shallow water for a long distance. That gives water more opportunity to pile up before reaching land. A narrow, steep shelf drops quickly into deep water. The same storm may produce a lower surge there, although waves can remain large and local features still matter. Place two identical hurricanes over two different shelves. Their wind, pressure, speed, and track are unchanged. Only the seafloor moves. Over the gentle shelf, the water surface rises earlier and higher. Over the steep shelf, more of the circulation remains in deeper water until closer to shore. Much of the Gulf Coast has broad, shallow shelf water. That geometry helps explain why large Gulf hurricanes can drive serious surge across wide areas. Small-scale channels, barrier islands, sounds, and estuaries add another layer. They redirect flow and create local peaks that a smooth coastline model would miss. Transform the flat map into a side view ramp. One incoming water slab stretches and rises. The other drops beside a steep wall. Same storm, different ocean floor, different coastal height. This is also why historical surge from one place cannot be copied directly to another coast. Even if two storms share a category, the underwater landscape changes the flow before it touches land. Local elevation then changes how that height becomes inundation. Coastlines are not straight. Bays curve inward, capes point outward, and islands divide the flow. That geometry decides where moving water can spread and where it must crowd together. A concave coast acts like a funnel. As the opening narrows, water occupies less horizontal space, and the level can rise. Long bays and estuaries can guide surge inland. If the wind aligns with their length, water is pushed toward the head of the bay with fewer escape routes. Barrier islands can block part of the flow, but inlets concentrate currents. Water may enter sounds and then struggle to drain while onshore wind continues. The storm's angle of approach changes which sections receive sustained onshore wind. A small track shift can rotate the push toward or away from a vulnerable bay. That is why maximum surge usually does not form as a uniform ring around landfall. One side can receive a powerful onshore flow, while the other side experiences offshore wind. Fold the coastline around the incoming current. Cyan water lanes squeeze together, turn gold at the narrowest point, and stack inside the bay. Now shift the hurricane track slightly. The wind rotates, the strongest onshore corridor moves, and a neighboring bay becomes the funnel. A small forecast error in the center can therefore produce a large local difference in surge. Hurricanes are often described as sucking the ocean upward with low pressure. Pressure does raise the sea surface, but that effect is usually much smaller than the wind-driven pileup near land. Atmospheric pressure is weight. Lower the weight above one patch of ocean and the water surface can rise slightly, much like a flexible cushion expanding when a hand lifts. A rough rule is about 1 centimeter of sea level rise for each millibar of pressure drop before the surrounding ocean adjusts. Even a deep pressure deficit gives a rise measured in tens of centimeters. Major storm surges are measured in feet or meters. Strong onshore wind acting across a wide, shallow shelf supplies most of that much larger displacement. Pressure still belongs in the model. It affects the background surface and the wind field, but it cannot explain the full timing, location, or height by itself. This also breaks the idea that category directly predicts surge. Surge depends on wind, size, motion, shelf, coast, tide, and waves. Central pressure alone leaves most of that system out. Lift the pressure lid and watch the ocean rise a little, then switch on the broad onshore wind. The small pressure bump becomes a towering coastal wedge. The pressure explanation persists because the eye and its low reading are easy to picture. Wind stress is distributed across a vast moving footprint. It is harder to see, yet it performs most of the work that piles water against a shallow coast. In September 2008, Ike crossed the Gulf with a large and expanding wind field. Its broad circulation began pushing water toward the United States coast well before landfall. Higher than normal levels appeared around the Gulf as the storm moved west. The signal migrated from Florida, then along Louisiana, toward the upper Texas coast. NHC training material notes that waves set up raised water along the Texas coast nearly a day before Ike made landfall. Conditions deteriorated while the eye remained offshore. Late on September 12th, an NHC discussion reported water already 9 to 12 feet above normal across a large part of the northwestern Gulf, including Galveston Island. Ike's center reached the Galveston area early the next day. By then, the coastal ocean had spent many hours under broad onshore flow. Surveyed surge in the hardest-hit areas was generally around 15 to 20 feet. Tide gauges and high water marks showed how unevenly that water spread through bays and low terrain. Run the clock backward from landfall. The eye retreats offshore, but the waterline stays high. The surge timeline begins long before the center crosses zero. Ike also shows why a large storm's effects can reach well beyond the forecast center. Water levels rose around much of the Gulf as the circulation moved west. The local coast responded when the wind field aligned with it, not when a ceremonial landfall occurred. As hurricane wind crosses open water, it builds waves. Near shore, those waves slow, steepen, and break. Breaking does not only throw water forward for a moment, it transfers momentum into the nearshore zone and can raise the average water level there. That persistent lift is wave setup. Individual waves then run up above that already elevated level. Surge, tide, setup, and run-up occupy different layers, but a building experiences their combined reach. Repeated waves erode dunes and undermine structures. Once a protective ridge is cut, later water can move inland through the new opening. Long-period waves can arrive ahead of the strongest local wind. Their setup adds to the reason coastal water may rise before the eye arrives. Forecast systems calculate these pieces with different models and grids, then communicate the expected inundation rather than asking people to reconstruct the stack. Build the water column from the bottom: tide, surge, setup, and a breaking wave on top. The line that reaches the building is higher than any single layer. At the structure, the difference is physical. Surge raises the platform on which waves operate. A wave that would have broken offshore can reach a wall, foundation, or dune. The elevated base allows each impact to strike farther inland. Coastal cities normally drain downhill toward rivers, bays, or the sea. Surge reverses that gradient. Outfalls that should carry water away meet a higher ocean pushing back. If heavy rain falls at the same time, fresh water accumulates behind the coastal surge. Pumps and drains work against a rising boundary. Rivers can carry rainfall from far inland toward the same coast. Their peak may arrive after the strongest wind, extending the flood beyond the hurricane's passage. This is compound flooding. Ocean water moves inland while rainfall and river flow try to move seaward. The flows meet in streets, canals, wetlands, and estuaries. A slow storm makes the overlap worse by extending rain duration. A large storm can maintain onshore water levels across several tide cycles. The exact result depends on drainage design, levees, elevation, soil, and the timing of each component. Two neighborhoods a few miles apart can follow different flood histories. Animate both arrows at once. Gold surge enters from the coast. Cyan runoff descends from inland. They collide at the drainage gate, and the water surface rises on both sides. When the wind shifts offshore, coastal water may begin to drain, but the inland flood can keep arriving. The sequence can reverse currents through canals and passes more than once. A single peak timestamp misses that evolving exchange. The National Hurricane Center uses storm surge models such as SLOSH, which stands for Sea, Lake, and Overland Surges from Hurricanes. The model moves water across detailed basins and coastal grids. It takes storm track, intensity, size, and forward motion, then applies those winds and pressure to the ocean. Bathymetry, elevation, barriers, and water pathways shape the response. Because the future track and size are uncertain, forecasters run many plausible storms. An ensemble reveals places that flood across a range of scenarios. The public inundation graphic shows water depth above normally dry ground. It is built to answer the practical question: where could life-threatening water reach? A storm surge watch generally means life-threatening inundation is possible within the specified area, commonly within 48 hours. A warning commonly covers danger within 36 hours. Local officials turn those forecasts into evacuation zones and timing. Those zones account for roads and community logistics that a national ocean model cannot decide. Start with a single forecast track, split it into an ensemble, run every path through the same coast, and merge the results into one depth map. Uncertainty becomes a usable boundary. The map is intentionally conservative in how it communicates depth and location, but it is still a forecast, not a promise. People should use the latest official product and local orders because small changes in track, size, or timing can move the highest water. Return to the first image. The hurricane remains offshore while the road floods. Nothing has arrived early. The broad wind field has been working on the ocean for hours. Wind transfers momentum across a large area. The continental shelf compresses the flow. Coastline geometry funnels it. Tide and waves lift the final level. Low pressure adds a smaller rise, while rain and rivers can block drainage from inland. Each layer follows its own clock. Ike made the timing visible. Water rose around the Gulf and along Texas before the center reached land because the moving ocean was larger than the eye. Landfall marks where the center crosses the coast. It does not mark when hazards begin. For surge, the loading phase starts offshore and can close roads before the strongest wind. During a real storm, use official surge forecasts and follow local evacuation orders. Do not wait for the eye, a category change, or visible waves at your street. The ocean rises before the hurricane arrives because the hurricane is already there in the form that matters to water, a vast wind field pushing against a coast that has nowhere else to send it. That reframe changes the countdown. The relevant arrival is not the eye at the shoreline. It is the onset of sustained onshore flow across the shelf. Once that begins, the ocean can start closing the exits people expected to use later.